Hello. Okay. This might be kind of like sporadic, but I feel like if I can't meet up with you tomorrow, this might be easier. I have the thing pulled up and I'm just kind of going to go like page by page. Hopefully, this isn't too long of a video, but yeah, I'll try and make it like a little more common sense because I know sometimes they explain it confusing. Um, Basically, so the first thing that you need to understand is the null hypothesis and like what it means in this like statistical situation. So, to understand most of it, at least this lecture, the null hypothesis is the most important. So, null, think of it as like dull, indifferent, boring, plain, because the null hypothesis basically means that there is no difference with whatever it is. So, you reject the null, that means it is significant because it's not a dull, boring null hypothesis. And if you fail to reject it, that means that you failed to prove anything happened with the null, which means that there is no significance to the data. That sounds kind of confusing, but that's kind of like the most important part you need to understand for this lecture, just because understanding that null means it's insignificant kind of is the background for this. So once you understand that, also, again, they're always going to say it, never accept it because accepting it means that there's a 100% possibility, whatever. So looking at this statistical inference, there's a confidence interval and there's hypothesis testing. So confidence interval basically means like how confident you are that something is accurate, like how confident you are that your results are accurate to the bigger picture. So descriptive, I'll kind of get back into that, but I'm going page by page if this feels kind of like back and forth. But descriptive statistics, it says here, used to numerically describe and summarize collective data based on a sample. So let's say you have 10 people. Descriptive is 5 people prefer red over blue and the other 5 prefer blue over red. So that's a 50% chance people like blue, 50% chance people like red. That is descriptive statistics because you're basically describing the data that's in that sample. The inferential statistics is basically, do we think that this 50% blue is actually accurate to the entire population because you're only using a 10-person sample. So if the population is actually 1,000, how many people are actually going to be choosing blue versus red? Than 50%. So if we're looking at 1,000 people, it could end up being 30% blue. It's just because that 10 person range is so small that there's not actually an accurate representation. So descriptive is what's actually there, and then inferential is how accurate would that be if we were to size up to the actual population we're looking at rather than just the sample size. Okay, so based on the size of the sample, makes it more accurate. So if there's a bigger sample size, you're probably going to be more accurate to the population than if it was smaller. And then looking at the two different types of statistical inference, there's confidence interval and hypothesis testing. So confidence interval, it says here, method used to estimate the range within which we expect the true prevalence to lie based on percent level of confidence. So basically, how confident we are that our like estimated percentage or example or whatever it is actually lies within what the actual possibility is. So they use it here on the graph. The calculation is like 48% to 62% is like the interval range, the confidence interval. So, oh, this is hard to explain. Okay. So, some of these numbers you can't, there's no like they don't expect you to understand what's behind it, more of just like understanding the numbers. So like for example, the confidence level, they always have it at 95%. Don't ask why, we don't know why, it's just 95%. So the calculation that they use, standard or whatever, is that they want 95% confidence that your data will land between 48% and 62% of the range, or like the average. Again, the 48 to 62%, it doesn't make sense, because if you're thinking about why it's actually there, you just have to remember that if it lies within those percentages, then the confidence level is like 95%. That's kind of irrelevant, to be honest. That's confusing. Don't think about it like that. Just know 95% is like the percentage. And that goes back to the p-value, which I will get into. Okay, so with the confidence interval, because we're using a sample size and not the whole population, so let's say the 10 people that did blue versus red versus the 1,000 people in the actual population, there's, no matter how many times you do samples of 10 people within the 1,000 or whatever, there's always going to be an uncertainty that, like, there's always going to be an uncertainty of the actual value. So no matter how many times we do it, however close we get, there's always going to be, it's never going to be 100% true, because it's just like not possible. And so that like variation between the lowest number or the highest number of odds or whatever, like the variation between the results we get, that's like the standard error. And having a larger sample size, that standard error gets smaller, because with those 10 people, let's say, if we keep doing that, 50% people choose blue, 50% choose red, that's like not going to be as accurate over if you're looking at a population of 1,000 people than if you were to do 500 people or 900 people and have them choose out of that 1,000 person sample, because then you're getting a more accurate like expectancy, because it's like a bigger number. Like I feel like that's kind of common sense. Like that part I feel like should make sense. Sorry, I'm trying not to make this choppy. That's why it keeps cutting. But basically, with the whole standard error concept, the larger of a sample you have out of that total population, the estimated result you get is going to be the closest to that true prevalence. So think large sample, small standard error. And then if you have a small error or a small sample, then there's going to be a wider range of values of estimates that make it further from the true value. So a smaller sample means a wider standard error. And then for the exam, confidence interval is going to be given to you. It's going to be a number that like you're not going to have to calculate any numbers. Like it's just going to be given to you, and then you're going to have to like look at that number and understand if it's significant or not, is basically the concept of this exam and like whatever. So going back to the 48 to 62%, again, this, I feel like this part of it doesn't necessarily matter, but like if you look at that this graph, for example, that is gonna, wait, hang on. Okay, I don't know if you can tell, but if you look at this graph, for example, the true prevalence right here is that 50%. So the range goes from 48 on this side to 62. 50% is like that true number, meaning that's the actual data. If you look at these little lines right here, so the dots between the lines are what the confidence level was that the researchers came up with. So yeah, stick with me here, okay? The dots themselves are the researchers' estimated, like their final estimate. Each side of those lines is that standard error. So this one, for example, the one that this arrow's at is what? 25 and the other side is like 45. I don't know if you can kind of tell what I'm talking about, but it doesn't really matter. Either way, the line itself is the standard error, or like the range, I guess you could say, and then the dot itself is the actual value that the researchers came up with. Now, the confidence interval is from 48 to 62. So basically, what this means is that if it's not crossing that middle 50% true line, that means it's significant. So, like, this one right here is significant because it's not crossing that line. And it'll make more sense when I talk about the actual, like, confidence interval values rather than just this graph where it's, like, percentage. But just know that, like, if it falls within that 48 to 60%, that means that it's an average, which, jumping ahead, means there's no difference, aka a null hypothesis. Stick with me, I promise. I promise. So this second slide's talking about the 95%. That doesn't matter, just know that 95 is like the number they use. The wider the interval is, the more unstable. So that line I was talking about on the graph, the wider it is, that just means that, like, that dot can fall in any of that spot, which means it's just less accurate. You want, like if it's 1 to 5, having a 3 with the range between 1 to 5 is a lot less than having a 3, but the range is 1 to 100. That means it could be anything in that, so it's, like, all over the place. So you want that interval range to be smaller. So now, if we're talking about confidence interval, so this is the slide I'm looking at right now, if this helps. I feel like this is really hard to see. Okay. This is so tragic, I'm sorry. Okay. So the importance before I get to this part, the importance of this is if you see a number labeled with CI, that is different than if you see it labeled with OR, okay? So if it has a value and there's an OR next to it, here, let me see. So t-test is the same thing as CI, okay? I'll put that to start. But, like, do you see how this is OR and this is t-test? Make sure when you take the test, you're looking at that because they are different. Anyways, going back to the confidence interval, all you need to know, if there's a graph labeled whatever numbers, there's going to be a center line on the number 0. Confidence interval is 0, okay? Remember that. With that whole line thing, like I was saying, the actual numbers that they put are not going to matter. They're going to be examples. It's irrelevant. However, if it crosses that 0, that means that it's not significant because it's falling within that 50% range, or that 48 to 60% range. Again, not important. If it crosses the 0 line, if it makes a cross with the 0, that means it's not significant. You need a value range that's either above that 0 or below that 0 for it to be significant, I guess. Like, I don't have another word for it, but let me hang on. But here's the graph. This is 0, -1 through 3, 1 through 3. If they give you, this is also, like, hypothetically, like 40% to 60%. Doesn't matter. Ignore, yeah, you know what? Ignore I just said that, okay? 0. This is confidence interval. If you see this, that means it's 0. So basically, if they give you a range that's from it could be any number. So -1, for example. This marker sucks. And the other range is, or the other number is 2. That means it's crossing that line. That means it is not significant, okay? Now, if you get -3 to -2, that does not cross this line. That makes it significant. Oh my freaking God. That makes it significant, okay? I feel like this is common sense, but some people get it confused. But just remember, the most important part of this is that this is confidence interval. Now, the lower limit is the lower number, and the higher limit is the upper limit. And, okay, so let's say I have this again. So this is the lower limit because it's the lowest number. This is the upper limit because it's the highest number. And then the actual like test result would be whatever line they have here in the middle. So that could be here, it could be there, it could be anywhere. It doesn't really matter. But this is like the actual range, and then those are like what those dashes mean if you were curious. So then on the test, they're going to give you examples where this marker works better. It says it has it here, but it's like CI equals 1.98 to negative 1.6. So if you're looking at an example like this, because it goes from positive to negative, that means that if it were hypothetically on a graph, that means that it's crossing that line and it's not significant. If it stays positive, so if it was 1.98 to 1.6, that means it's not crossing that zero line, which makes it significant. Or if it's the same thing for negative, if it stays negative. So negative on this one, it says negative 0.2 to negative 3.8. That means it's significant because it doesn't cross that zero. And I feel like I reiterated that a lot, but I know that people got confused with that in my class, so that's why I'm saying it so much. And then, for example, like on this one too, there's the actual value, and then there's the range. So when it gives you the range, that's pretty much all you have to, if it gives you the number and the range, you're pretty much just looking at the range, because if that range crosses the zero, then of course it's not significant. Now, looking at odds ratio, so it says here it's used with retrospective data, which is case control. So you have a disease state, you want to see if there's an association with a given cause. So what are the odds that someone's been exposed to something given that they have the disease? So honestly, I haven't taken this test in a minute. So the whole case control retrospective stuff, it's been a minute. So yeah. The easiest way I can teach you this, odds ratio, pay attention to the label. This is OR, this is not CI. OR, it is the exact same thing as confidence interval, but instead of crossing 0, it crosses 1. That's it. That's literally it. So when you're looking at the numbers, make sure you're looking to make sure it says confidence interval or if it says odds ratio, because odds ratio is the exact same thing, but that starting value, that point on the graph is 1, it's not 0. Confidence interval is 0, and confidence interval is also the same thing as t-test. So if you see a t-test number, that is confidence interval, meaning making sure it's not crossing 0. Let me look at this. I'm backtracking a minute. Okay. The t-test is not the same as the confidence interval. The confidence interval is the value, and then based on that value, it's either for a t-test or an odds ratio. I hope that makes sense. So a t-test compares the two averages, and the odds ratio, they're just different types of tests. Okay, wait, sorry. I don't know why I'm getting myself confused. Basically, with a t-test, the confidence interval, if it crosses 0, it's not significant. But then for an odds ratio, the confidence interval, if it crosses 1, it's not significant. So the 0 and the 1 still stands the same. It's just if you see a t-test like as the number, that means you're looking to see if it crosses 0, and then if you're looking at the OR, you're looking to see if it crosses the 1. So basically what I said, it's just don't think of CI and t-test being the same thing, because they're technically not. now going on to the p-value stuff. Okay, yeah, sorry. This like is an example. So the confidence interval is the actual range, and then the number is what the actual value is. But depending on if it's odds ratio or t-test, that tells you if it's significant or not, because if you're looking at an odds ratio, if it crosses 1, that means it's insignificant. So this is the answer for the top. Like the top one's the answer. But if it was t-test, for example, you're looking at something that crosses the 0 line to be insignificant. Other than that, it's significant. I hope that didn't just throw you off. I apologize. Okay. Hang on. Let me look at this really quick before I film. Okay. Now, before we get into the p-value, we're going back to the hypothesis and the null hypothesis. This is what I said before. The null hypothesis means there is no statistical significance. So, if there's no significance, aka it crosses that 0 if it's t-test, or if it crosses that 1 if it's odds ratio, that means we are not finding any statistical difference, meaning that we fail to reject. Let's say it doesn't cross that 0, it doesn't cross that 1, meaning there is a statistical difference. That means we reject the null because we are rejecting the fact that there's no difference. That means we found a difference, which is good. Or, well, I guess it depends on what you're researching, but whatever. So the p-value essentially is like seeing if there's actually a true difference or if it's just within that range based on by chance or whatever. So thinking of that 95% confidence, which again comes from wherever, if you think of that as a decimal, that's 0.95. 1 is our total, for example. 1 is our total in any situation, 100%. So p-values are normally set at 0.05. 0.05 is a 5%. So if our confidence is 95, if it falls within that 5% or less, that makes it significant. And sometimes the p-value can be 0.01, also 1%, or 0.001, which is 0.1%. I think that's what it is. Okay. Yeah, that's what it is. Okay. So that's kind of where that decimal comes from, is like it's the opposite of that 95% confidence. So p-value, also known as alpha level. So if they hit you with an alpha level and they're like, what's the alpha level, or is this alpha level significant? Don't get confused. It's literally just a p-value. It's the same thing. So p-value is normally set at 0.05, aka 5%. So when you're looking at significance, you're looking at anything less than 5%. 5% or less. So if it's below, that means that our results are significant, meaning that we can reject the null because it has a significant Wait, I literally just blanked. Result. Oh my god, jeez. But if it's above that 0.05, meaning it doesn't fall within that 5%, means it's not significant, which means we fail to reject because that means there's no difference. I feel like if this is confusing, I'm so sorry. But I'm going to keep going. If you have questions, let me know. So the smaller the p-value is, that means there's stronger evidence of a statistical difference, meaning there's stronger data against having the null. So you have it's kind of like less, it's like that small like range, like the less percentage you have of inconfidence, that means you're more confident with your answer, meaning you're most likely going to be more correct than you would be. Because if you're having a 95% confidence level and it falls within that 5% of like correctness, this is just getting sad, I'm sorry, then that means it's good, right? That means it's significant. So if it's 0.04 out of the 0.05, that means it's significant, but it's still more, there's still more of a range than if it were to be 0.002 out of the 0.01, if that makes sense. I feel like that does make sense, but me explaining that's not helping. But yeah, the smaller the number, obviously. So if there's a p-value, so I'm using the examples on the slideshow, but if the p-value is set at 0.05 and the result is 0.03, that means it's significant, aka we're rejecting the null. But if it's set at 0.05 and we get a 0.06, then it's not less than that 5%, so we're gonna fail to reject because there's no significance. Again, if they hit you with the alpha level is set at this, and this is the test level, remember, alpha level is P level, so it's the exact same thing. They're going to try and throw you off. It can be anything lower than 0.05 is technically a significant p-value, but you have to make sure you're looking at what it's set at and what the actual results are, because if it's 0.04 is the test result, but the p-value is set at 0.01 instead of 0.05, then it's insignificant because it's bigger. It cannot be bigger. It can be the same as if it's 0.05 and the test result's 0.05, then it's significant. But if it's anything more than that, then it's not significant. So again, significance means that the null is rejected. If it's not significant, then we're failing to reject. So fail means there's no significance. So like fail is no and fail's bad. I don't know. Okay. So this whole slide, this next one, I'm on slide 22 by the way. In percentage is basically what I was saying with the 0.05 represents that 5%, which is like the 5% remaining from the 95% of confidence. So the way that they're saying that they're putting it is that the significance level is that 95% or 0.95. So the p-value is the small one and the significance value is 100 or 1 minus that decimal. So if you're doing percentages, 100 minus 5%, 5 being the 0.05 p-value. If you're doing a decimal, it's 1. The total's 1. So then it's 1 minus the 0.05 p-value, making it that remaining number the significance level. And the significance level means their certainty that the results are not due to chance, meaning that they're more accurate. So 95% means that they're 95% certain that these results are true and not just based on luck, because association and correlation don't actually mean like cause effect or whatever. And that's basically like what this whole chart is just like example numbers. So then this is like the last part, and if you understood the previous parts of this should be pretty easy. It's more of like a thinking game when you're actually reading examples about it, because a lot of this is just like read the question very slow because they'll try and trick you, and then picking apart what's actually happening. So maybe like use a scrap piece of paper or whatever. So the errors is, there's 2 errors: rejecting the null and failing to reject the null. The errors for this would be if you reject the null and you're wrong, or if you fail to reject the null and you're wrong. So it's the opposite of what you thought. So where did that slide go? Okay, alpha, A, first in the alphabet. Alpha, first in the alphabet, 1. Type 1 error is an alpha error, okay? Alpha error is, why am I being, okay. What? Okay. And then the other one is beta error. So B, second letter in the alphabet, type 2 error, okay? Just remember that. It shouldn't be too hard. Okay, type 1 error, alpha error, is when we reject the null, meaning we think there's significance to our value, but in reality, there's not. So think of it this way. Alpha value is the same as a p-value. So if we're thinking of an alpha error, we're thinking p-value error as in like, oh, the p-value is significant, which is wrong. So if you get a type 1 error / alpha error, I'm trying to mix it up so that you kind of get used to it. That means that we were like, oh, that was a statistical difference. That means that like this affects whatever, but in reality, there's actually not a difference. So I don't know how else to make that more simplified other than think of the p-value as significant, alpha as significant. Alpha error means that the significant is not actually there. And then type 2 or B is the opposite. So we don't think there's any difference happening when in reality there actually was a difference. So if we fail to reject, meaning we think there's no difference, we're failing to reject the null / the dull result, that means then there's actually no difference. So the examples they use are kind of confusing, and I'll admit that. However, those types of examples are the ones that are going to be on the test, which is why the tests are normally pretty hard because their wording's bad. No offense to them, but that's like what it is. So when you're reading examples, so I'll read this theoretical example of an alpha error and then I'll tell you like kind of what to pick apart. So theoretical example, let me read it. The conclusion was incorrect. Oh wait, that's the second part. Okay. An investigator conducted a study of the effectiveness of Listerine in reducing the incidence of gingivitis among entering dental hygiene students at UDM. She concludes in her manuscript that the Listerine is superior to placebo at reducing gingivitis among entering dental hygiene students. So right off the bat, she thinks one is better than the other. That's an automatic example that she thinks that there's a significance. This means that if she thinks there's a significance, it's an alpha error because, okay, well, if she thinks there's a statistical difference, that means that if we kept reading, if we kept reading and found out that there's no difference, this is an alpha error because if you look at her conclusion thinking that one's better than the other, that means she thinks it's significant, and if it's not actually significant, that's an alpha error. So making sure like you're reading for that one is superior or in conclusion we found no difference, then I hope this is making sense. I'm so bad at explaining, I'm sorry. So then continuing on with this example, without the investigator's knowledge, some of the hygiene students had supplemented their Listerine using Paradex. So if a question is asking you what type of error, then you're looking for, if they say superior, that means that's an alpha error, or one's worse than the other, it's an alpha error. If the person is concluding that there's no difference or one's not better than the other, but the question itself is asking what type of error this is, then you would know if the person doing this research finds nothing significant, that means it's a beta error. If the question, though, is asking, I don't think they would ask, but like, is this significant or not? If they say they find a difference and then the p-values align or whatever and the confidence intervals align, that's when you know your answer is like yes or no. Like, do you know what I mean? I don't know if that makes any sense. But then continuing on, the conclusion was incorrect because it was actually the Paradex that had decreased the incidence of gingivitis rather than Listerine. So the investigator had concluded that the Listerine was useful when in truth it wasn't actually more effective. So they thought there was a significance and there wasn't. And they were supposed to fail to reject. but instead they rejected. And then for the example with type 2 beta error, we conclude there's no difference when there is a difference. So this example, blah, 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 Listerine, whatever. She concludes in her manuscript that the Listerine is no better than the placebo. So when you read is no better, has no, is not different, is not better, is not worse, that means that she found no significance. But if the question is asking for an error, if she found no significance, that means that there actually was an error, and that would make it a beta error or a type 2 error. So just make sure you're kind of reading the questions like that. And then this, okay, I'll read a class exercise. I don't know if they give you the answers to this, but I'll just go over it anyways. After conducting an investigation of the relationship between smoking and periodontitis, an investigator concludes that smoking is not significantly associated with the development of periodontitis. So for the null hypothesis, they are not me pausing. Okay, I'm sorry. So they conclude that smoking is not significant. So for the null hypothesis, they'd be failing to reject because they think there's nothing significant about it. Now it's asking what type of error could have possibly occurred. So they think no difference happened. But if there was an error and something did actually happen, that would make it a type 2 error because they thought there was no difference when there actually was. And then the second example, rinse C is effective in preventing gingivitis but causes severe burning of the gingiva if used for more than a week. An investigator wants to know if rinse D, which does not cause burning of the saliva, is just as effective as preventing gingivitis. The study type, I don't know because I have not reviewed those slides. The null hypothesis, if you were to make a null hypothesis, if that's what that's asking, would be like, well, I'm forgetting how to make a null. There's no difference. Yeah, there would be no difference between rinse C and rinse D in the effectiveness of preventing gingivitis. And then the primary error type. If they're looking for if it's just as effective, I'm not answering this one. Sorry, guys. I don't know. And then this last slide, I'm sure you guys know at this point, but correlation implies two things can be moving in the same direction or crossing in a way that seems like it's related, but it's not. They just happen to be somehow related. Like an example would be sunburns, and I actually had to look this one up. This is a good example. Sunburns and ice cream sales. Ice cream sales are going up, and sunburn numbers are going up. So they're moving like this. So they're correlated because people that are buying ice cream are outside. People that are getting sunburn is because they're outside. But there's not actually a relationship between buying ice cream and getting a sunburn. Association implies that there's a close relationship between two or more variables, but that doesn't mean one's causing the other. So for in this example would be diabetes and periodontal disease. People that have periodontal disease also most of the time have diabetes. People that have diabetes also have a higher risk of periodontal disease, but periodontal disease is not causing diabetes, and diabetes is not causing periodontitis, because you can have one or you can have the other without having both. And then causation is one's causing the other. So this one says H1N1 virus and swine flu. I don't know nothing about that. I don't know. It causes it. I don't have an example for this one. I just feel like it just makes sense. I don't know. Being up for a lot of hours causes you to be tired. Like, I don't know. Is that a bad example? It might be. But anyways, if this was long, if this was confusing, ask me questions. I don't know. This is the best I could do without being like obviously one-on-one, but I wanted to give you some sort of review, because if I can't meet up with you, obviously, like, hopefully this helps a little bit with my explanation versus the teacher's explanation. Again, I will try and cut this up so it's not as like pausey and confusing and like isn't as long. But just ask me any questions. Hopefully this helps a little bit. Hopefully it wasn't too confusing because I didn't really prepare like a speech or anything. But yeah,